everyone. Common Lisp supports an interactive development style that I think is extremely cool. And I thought it would be fun to demonstrate this development style in this screencast by playing around with making these little pictures called Identicons. Now, these Identicons are a kind of hash visualization. And Perig and Song wrote a paper about this, and they were concerned about hash visualization, that's hard to say, for a serious purpose, but we're going to use it for a frivolous purpose. Just as a quick refresher, a hash or a hash code is the output of a hash function. And a hash function maps some variable size, arbitrary data to some fixed size output. One hash function that you see a lot in the world is SHA-1 or SHA-256. Just to show you an example of what those things are, say we want to compute a hash of ABC. And there it is. And one of the characteristics of these cryptographic hash functions like SHA-1 and SHA-256 is that even a tiny little change to the input makes a big difference to the output. This is called the avalanche effect. So you can see even though all we did was change A to B, the output is totally different. Now, the idea behind hash visualization is that it's hard to look at these strings and compare them and remember them. And it's much easier for the eye to look at images and detect similarities and differences between them. So we're going to play around with making these things, which are derived from a hash of a username, and they're used on GitHub. You might have seen them. So let's get started with that. Let's make a package to play around in. Great. And now let's go into that package. Now, I guess to start out with, in order to do any hash visualization, we need some hashes. Now, unfortunately, there's no standard Common Lisp function to do cryptographic hash functions. And there doesn't happen to be one built into Clozure Common Lisp either. Maybe that's a subject for a future video or a future article or a future feature. So what we'll do is we'll call a C function to do the hashing. Now this relies on implementation-specific functionality, but maybe it'll be interesting to see that. So I am on a Mac, and I know from Googling and finding a man page that there's a function called CC SHA-256, and it's callable from C. Apple doesn't really want you to call these anymore. They've deprecated them. Their nice way to call hash functions is from Swift, but it's easy to call. It's easy to call C from Clozure CL, so we're going to just stick with that. And in order to see whether this C function is available to us, we'll use this function called external and see if it's there. This tries to just resolve an external symbol using the dynamic linker. And we see that it does in fact resolve. It's in this LibCommon crypto shared library. So that means that we can call it. So that's good. We don't have to do anything more. We don't have to open any shared libraries or do anything tricky. It's already there. We can already call it. So we'll use SHA-256. Not for any really good reason other than just if we used SHA-1, maybe that's not quite kosher because it's considered cryptographically insecure, although we're not really concerned about that. We're just here for fun. But we'll use SHA-256 anyway. And what we want is to get the hash of a string. Now, a Common Lisp string is not the same thing as bytes. So we have to encode the Common Lisp string into some bytes so that we can pass it to this foreign function. And we do that by the function encode string to octets. So we'll encode our string using a particular external format. We'll use UTF-8 since that's pretty common. Okay, that's fine. Now, SHA-256 is called SHA-256 because its output is a 256 bits. It's a string of 256 bits. 256 divided by 8 is 32, so a SHA-256 hash takes up 32 bytes of memory. So we'll use that here in a minute. Now, we've got some bytes, but it's still not allowed to pass Lisp data directly to C data because Lisp data can get moved around by the garbage collector, and if a C pointer is still trying to point to the old place, before the GC moved it, it's going to be catastrophe. But it is a common desire for people to pass a pointer to Lisp data to a C function, at least for a little while. So we have a little macro to do that. It's called with pointer to iVector. And this is sort of a geeky internal name, but an iVector is a Lisp vector that just contains stuff like, characters or unsigned byte 8s or unsigned byte 32s, something like that. Nothing Lispy. You couldn't have a const cell or a hash table or a symbol or anything like that in an iVector. But our encoded string, a bunch of octets, that will be fine because octets is just going to be of type unsigned byte 8. Right, so that's going to give us an octet's pointer, which we can give to the C function, and that'll point to the data in octets. We also need a place to put the output hash data. There's a way to reserve memory that foreign code can refer to and that won't move with this stack block form. It starts with a % because it's sort of dangerous in some way. If you mess up, you could crash the list. But if you use it correctly, it's safe and it works fine. So we'll call that hash pointer, and that's going to be of hash size bytes. Now we need to call this function and pass it all the relevant data. We'll use the external call function for this because the interface database doesn't know about CC _SHA-256. That's all right. This is not too complicated. We're only doing it in one place. Now we pass these keyword value pairs in order to tell CCL what to do. So the first parameter is an address, and that's the data that we're going to process. So that's our octets pointer. The next thing is the length of that data, and that will be unsigned, I believe that ends up being, and that'll be the length of the encoded data. And finally, we need a pointer to the result. That'll be an address, and that's hash size. And the function happens to return a pointer, an address. We don't care what it is. It turns out that it's a pointer to the computed hash, I believe, but we're ignoring it here. Okay, so that seems like that ought to be okay. But now we've got the hash result in foreign memory. We need to get that back to Lisp. So we've got a copy. We'll call that output. And that's going to be hash size long. And that is of element type unsigned byte 8. And we just copy. And we use this get unsigned byte unsafe function. Signed byte, and that's the hash pointer at offset I. Fine. And we just return that guy. All right, fine. Let's see if that works. So see, I messed up already. At least that didn't crash. Oh, see, I made a mistake here. It's not hash size, it's hash pointer that we want there to pass to the CC. Okay, sorry about that. And that's what it is. We could try to replicate that at the shell prompt, but we're getting hex output rather than byte output. We can maybe try to convince ourselves that it's in the right neighborhood. So 186, that's what we've got there, and that's what BA is. So it looks like we're in the right neighborhood. But just to be sure, we can write a little debugging function just to print out the octets as hex digits. There's lots of ways to write this function. I'm gonna just map over the octets and call and use format to print a 2 wide 0 padded hex byte. Over the octets. All right, okay, so now if we say hexify, I think that's 2 ago, but we'll just, elevate it to new. There we go. That's capital letters, so not as easy to maybe compare as we'd like. So if we just put that there. Okay, and that's looking pretty good. So you can say string equal that and that. T, computer says T, we're good, that works. So our hashing seems like it is doing the right thing. Let's turn our hand to visualizing the hashing. As you can see, this particular icon is a grid and it's 5 by 5. So there's 5 by 5 pixels there. I mentioned, I believe, the website to generate these Identicons. And there's the source code for that also available. It's in JavaScript. I read this, and it turns out that the way they make the grid is they take the first 15 nibbles of the hash, and then for every even nibble, they turn on a pixel, and for the 0 nibbles, they leave it off. But here's the trick. The first 5 nibbles are used to set the center column. The next 5 are used to set these columns on either side of the center. And the last 5 are used to set these outside columns. So we need a total of 15 bits to set this 5 by 5 grid. So let's start with that. Let's see if let's write a function to compute those 15 bits from our hash. We'll call that Identicon bits, and we'll have a number of octets that we're going to get that from. So to start out, just let's see how many we have. We might as well be a little bit nice and say, well, we only need 15 bits, but bytes come in pairs. So we've got to get at least 8 bytes as input. So if we have fewer than 8, we're going to have to complain about that. Now with those in hand, we're going to want to return a bit array, or really a bit vector, as our output. So let's make that. So we'll call that grid. No, sorry, we'll call that bits. And we'll make that 16 elements long, just because we're going to be iterating over 8 bits, and it's easier. Make that, and we'll put a fill pointer on this so that it's easier to fill it in as we go. Okay, so now we'll iterate over the input octets. Let's see. Of which we're only interested in 8. And then we need to split that into nibbles. So our octet then is there's our octet. We want the high nibble. So we'll use LDB, and our byte spec will be 4 bytes long, starting at position 4 of the octet. And the low, same thing, except the byte spec is 4 bits at position 0 of the octet. That looks good. So now we just need to say if high bits even, we want to push a 1, so we'll vector push a 1. And otherwise we'll vector push a 0. Oops. Same thing for the low nibble. It's even, we push a 1. We could rewrite that, but this is clear, and it's not, there's no sense in being excessively clever. So that looks good. We'll return the bits. There. Let's see how that looks. Oh, didn't like that. What did I mess up? Misspelled fill pointer. Okay, there we go. So let's just take a quick look at that. So instead of hexifying that, we'll look at the Identicon bits. And there should be 15 of those. There they are. And we've got the hex right above there, so we can see is, you know, B, that's odd, A, that's even, 7, that's odd, 8, that's even. So it looks like that's doing the right thing for us. So now we've got these 15 bits. Let's go ahead and see what that looks like. So we'll write a function to build the grid, the Identicon grid here from those bits. So and we'll just be nice to our caller again if the bits are not 15, less than 15. All right. So our grid then is going to be a bit array. 5 by 5 type bit. And now it's a little bit fussy on how we do this, but just as a reminder, we're going to set the middle column from the first 5 bits, these columns directly to the sides of the middle column from the second 5 bits, and these on the outside from the last 5 bits. I'm going to paste a comment in here that I already made, just maybe to help out a little bit. So we'll just so here's what we'll do. We'll make a loop, and each time we set a whole row. So from the input bits, which is 15 bits long, we'll identify the center bit, and that's going to be bit 0. Maybe this would be easier if I just said aref. So that'd be the very first. All right, so that'd be in the first set of 5. We'll get the, what should we call these? The inner bit. That'll be 5 bits over. That shouldn't be so. That should be I. That'll be 5 bits ahead. And finally, the outer bit. Same thing. Only 10 bits ahead. So we'll go through 5 times, and it's as if we'll be running pointers down each 5-bit segment of the input bits. And let's see. Now all that's left for us to do is to just set the bits in the grid. So, so we just say, so we're going to set the columns of row I from left to right. So this one, row 0, index 0, we'll set that first, and that's outer bit. The next one will be right, inner bit. Good. Then center bit. Inner bit again. At column index 3. And finally, at column index 4, over here, the rightmost column in the row will be outer bit. And that's it. We'll return the grid. Okay. Does that compile? No, I misspelled something. Let's try it again. There we go. Just for the heck of it, just to see if it works. So what about, so given the bits, okay, we get this 2D bit vector. Now with this 2D bit vector, or I should say 2D bit array, we need to display that in a nice way. For testing purposes, let's go ahead and maybe display it as text. And then we'll see about displaying it as an image of some sort. So let's write a function just to show that grid, this bit array here, in a way that's easier for us to evaluate, easier for us to see. So let's see. We'll print the grid. Here's the grid. We'll make it possible to print to a stream. So what we need here is, let me see. No, we have the grid. We want to print it. All right, so let's start on a fresh line. And then we just have to iterate over it and print. So that's super easy. Okay, if it's a 0-bit, where you want to show just a blank space. And if it's not 0, we want to show some sort of block. And it turns out there's a Unicode character called full block. We don't have a name for it, but that's what it is. And when we're done with a row, we'll go to a fresh line. And that's all we have to do. Let's see if that works. So we've got in star here, oops, my history's all messed up. Let's see, print. And then we'll just put that in there and see what we get. Oh, all right, nice. That's what we hoped for. We can even play around a little bit and see some other things. Okay, that looks pretty good. Let's wrap that in a little bit of a nicer user interface, and we'll call that text Identicon. And what we want there is we want the string of whatever it is we're gonna hash, and then we'll provide the ability to write that to just some string. And the way we do that is we need the hash, so we'll take the hash of the input string. We need the bits so that we can make the grid. We need the grid, which we make from the bits. And now with the grid in hand, we don't have to do anything else except print it out. To whatever stream it was. Now instead of this big mess, we can just say write text Identicon ABC, and we get it. Nice. Let's see if we can make it generate SVG. SVG, I don't know very much about, but I went to a Wikipedia article, and there is kind of an example here that I was able just to copy from. So that's what I'm going to do. And I think we want the SVG to look just like this. Except write text Identicon, I guess we'll call it SVG Identicon. We need the same stuff. With SVG, we can specify a color. So why don't we get a hold of the hue, and we'll derive the hue. And now we have some fussing. So what else do we need? Well, with SVG, we need a viewport width and height. That's the physical area on the screen that the image is going to take up, I think. That's how I've been thinking of it anyway. We'll make that be 200 units. We'll make the height be 200 units. And inside the viewport, we'll have a coordinate system, and that coordinate system we'll make that run from 0 to 200. So we'll make just the coordinate system width be 200. We'll make the height be 200. And that looks pretty good. Now we need to put an SVG header. And that looks like this. And in fact, I'm just going to go ahead and copy it in, just because it's a little bit tedious. So nicely enough, we can put single quotes on these attributes, so we don't have to do a lot of escaping of the double quotes for the Lisp string. And we're gonna, so we've got to fill this in. So the view box, that's gonna be a string, and it's gonna look like this, and that's 0, 0 with height. And then, well, width, height, like that. Fine. Now we're going to wrap all our content in a group, because we're going to apply the color at the group level. So we'll do that. We're going to specify a CSS color here in the HSL color space. So we've got our hue. That's a floating point number, so we're going to fill that in there. And we're just going to use 40% and 80% as the values for the saturation and the lightness, so that will be fine. I don't think, what do I do here? I guess I need a closing parent. That's it. Just fill in the hue. Okay. Now we need to print out each row, setting the pixels, the 5 by 5 pixels appropriately. So we'll just iterate over our grid. And if the item is positive, we want to draw an SVG rect and add a row column to some stream. And I think that's it. We close our group. We close our SVG element. And that's it. I think that's okay. See how that is? Okay, so what to do? I think what I want to say here. I'm not really sure I have this viewport width and height right. I'm not sure I'm using the right terms. Identicon. I don't have Identicon hue. I didn't write that yet. Let's just hold on here for a minute. Cheap and sleazy way to comment things out, and we'll just make this be 0.2 for now. And now we need to write this SVG rect function. So X, that's the column index. So that's gonna, each pixel's 40 units wide. Likewise for the rows, those are the Y coordinates, they're 40 units. Width is 40, height is 40. So that's a single pixel, which is a square, 40 unit square. And then we just write the element out. X equals some value equals some value, height equals some value, and that's it. I think that's okay, and then that's just X, Y, W, H. All right, SVG rect 03 T. That looks okay. So here's write SVG. SVG Identicon. Well, let's try that. For our friend ABC. Let's see. Does this look okay? There's our header. There's our group. I guess that's all right. Close group, close SVG. Okay, let's write that to a file. And that should do the trick. Let's go here and what do we call it? Sample. Oh, and there it is. It's black. We don't have the color right. Is there some silly mistake in the SVG? Oh, here it probably is. Instead of, we want 40%, not %40. And we'll do that once again. Come over here and read. And there's the color. So we've done it. We can try another one, reload, and there we have that. So we're almost there. The only thing left to do now is we can derive a hue value from the hash function 2. Let's do that quickly. You're probably about ready to go do something else. So let's say default. Now the way they determine the hue value is they take the last 28 bits, of the hash, and they use that to derive a floating point value that goes between 0 and 1. So that's a little bit unusual. So in order to do that, we need at least 4 octets, because 4 times 8 is 32, and we need 28 bits. So 24 bits, which would be 3 times 8, is not enough. So we'll make sure that we've got at least that many. And say a few words if not. So now we need to get the last, we'll get our hands on the last 4 octets. So we'll just use subseq for that. And so that'll be subseq octets starting from 4 from the end. So that's our trailing bytes. And we need a 28-bit quantity. So what we're going to do, though, is first we'll make a 32-bit quantity out of those last 4 bits. And, this is just sort of the standard way. So we'll get the 0th element of the trailing. So that's 4 bytes in from the end. That'll be the most significant 8 bits. So we shift that over 24. And then we just kind of do the rest for the other guys. So number 1, we'll shift that over by 16. Index 2, shift that over by 8. Finally, the least significant byte, we don't have to shift it at all. That's 32 bits. We need 28 bits, so we'll make a mask so that we can just get 28 bits. So that's ASC. There we go. There's that. That's sort of a standard bit hacker trick. So fine. So we need it to be 1. So, well, first of all, we need to mask off the 32-bit. We need to mask off the lower 28 bits from the 32-bit value. And then we want to make a float. So if we do that, that'll get us a fraction between 0 and 1, and we want a float. So we'll convert it to a float, and I think that should do it. Let's see, what did I do here? Octets. Need that star. Okay, that'll be fine. And then earlier here, I noticed that I failed to implement that, but I have it now. Identicon hue. Did I spell it wrong? Yeah. Identicon hue. But now we should be able to see different colors other than this one. So let's see what we have here. So there's ABC. There's RME. We should have a different color for RME. But we don't. That's because I didn't pass in the actual hue. And now, there, I've got a different, now I'm getting a different color too. And that's it. So we've done it. We've implemented that same algorithm that website uses, and we make these little Identicons. So we derive all that information from the hash, and there it is. So I don't know if the way I do things is a good way to do things. Certainly not the only way to do things, but maybe this gives you a sense of a development workflow where you sort of get the computer to be more and more capable. It learns to do more and more things. So maybe I'll see you next time. So long.